In this video, I'm going to talk about some of the problems with the twin direction of causation model. The first limitation is statistical power. In general, the power of the twin direction of causation model is low, with thousands of relative pairs required to distinguish between the various causal models. Second, power is greatest when the two traits have different etiologies. For example, in the model on the left, trait A is influenced by common and unique environment, whereas variable B is influenced by additive genetics, dominance genetics, and the unique environment. The second consideration we need to be aware of is measurement error. Measurement error is a concern for all direction of causation models. Let's see how this works. Let's imagine that the true model is given by the path diagram on the left. What happens with measurement error under this model? Well, it's siloed away from all the other latent causes of variation. If you derive the expected covariance between the epsilon variable and any of the other latent sources of variation, this covariance is zero. In other words, error variance doesn't feature in any of the expected covariances between the variables, or between twin 1 and twin 2, or in the all-important cross-twin, cross-trait covariances. The problem, however, is that this model as written involves estimating 10 parameters, 3 ace paths for both variables, 2 parameters for the feedback loop, and then 2 error variances. We've discussed how we only have 9 pieces of information, and so this model is unidentified and can't be fit to our data. In contrast, let's see what happens when we don't account for measurement error in the model. Let's imagine that we fit the direction of causation model on the right-hand side of the slide. Here, measurement error is no longer explicitly modeled as part of the model. The good news is that we are estimating 8 parameters, ACE paths for both variables, and 2 parameters for a causal feedback loop. Not only is this model identified, it can be tested against the general bivariate model. But we have a problem of measurement error. Where does it go? Well, it doesn't just disappear. Instead, it gets absorbed into the latent E unique environmental variance components. This is a problem in causal models because this error variance gets transmitted through the causal paths to the other variables in the model. This means that the expected covariance between variable A and variable B is now a function of measurement error, and this shouldn't be the case. If you think about it, this shouldn't be possible in reality. If you imprecisely measure variable A, this shouldn't have any consequence on the values of variable B, even if variable A is causal for variable B. So in summary, the reason measurement error is an issue is that unmodeled measurement error can contaminate estimates of the unique environment, and then this error variance can be unintentionally transmitted from one phenotype to the other, and then back again if a feedback loop is present. One solution is to fit only one direction of causation, say from variable A to variable B, and only one measurement error term, in this case, for variable YA. The fact that there is only one causal path, in this case from variable A to variable B, means that any unmodeled measurement error variance in variable B will not be transmitted back to variable A. Likewise, any unmodeled measurement error in variable YB will be subsumed in latent variable EB. This will bias the estimate of the unique environmental variance component for variable YB, but it won't bias estimates of the causal effect of variable A on variable B. Perhaps a better solution is to use multiple indicator variables for both variable A and variable B in order to model the effect of measurement error. This could either be longitudinal data or different indicator variables that index the same latent variable. In this model, we have two indicator variables for traits A and B. This allows us to silo measurement error variance away from the latent A, C, and E variables. Whilst an improvement, this doesn't solve all our problems, since we are still making some assumptions with respect to the structure of the measurement error. For example, this model assumes that the different measurement error terms are all uncorrelated, which may not reflect reality. The last problem I want to discuss concerns what the direction of causation twin model is capable of testing. The direction of causation model is only useful for testing strong hypotheses regarding causality. This means testing the hypothesis that the only source of covariance between the variables A and B is due to the causal effect of one variable on the other. In other words, the model assumes that there is no latent confounding between the variables due to genetics or the environment. That's a pretty big assumption and may be unrealistic for most pairs of traits. Finally, our model makes all the usual assumptions that are common to twin studies. For example, with MZ and DZ twins, we can estimate at most 3 sources of variation per trait. We also assume no G by E interaction, no GE covariance, that the equal environments assumption holds, and many other assumptions. So what are my thoughts on direction of causation models? Well, I think that related pairs of individuals, like MZ and DZ twins, can yield information about causality, even in the absence of longitudinal data and experimental information. This information is contained in the cross-twin, cross-trait covariances. However, the twin direction of causation model makes some pretty strong assumptions that may not hold in reality, particularly with respect to latent confounding and measurement error. Therefore, the model should be employed with care. If you are interested in how observational studies might be informative for causality, then please check out my other videos on Mendelian randomization on the workshop site. I'll finish with some references that folks will hopefully find useful.